Hello, so basically we are going to show the writing robotic arm. So this is my CAD model in which I have made a writing robotic arm using 4 motors. So this is basically a 4 DOF writing robotic arm, but this motor is only used for the lifting of the pen purpose. And right now we are not going to use this motor because if we need some extra workspace or we are unable to reach some point, then only we are going to use. But we are going to use only this motor and this motor. So we are going to simulate this CAD model into MATLAB's Simulink software. So using tools, I have added it in the sim mechanics link folder. So I have added in the sim mechanics link, and then I have exported this model in the sim mechanics first generation. So in the MATLAB folder, so the files of STL files of the whole assembly is created in the Simulink software, and then after putting mech underscore import, we can import the CAD model into the Simulink software. After browsing this XML file and where we have saved, so we can import the CAD model. But I have imported it already, so we're not gonna do the same thing again. After importing, we're gonna find this kind of assembly. Our assembly will be looking something like this, wherein the environment is connected to the root ground, is welded to the root part, and is connected to the base assembly. Where there is a weld joint like this one present here, this present here, there is no relative motion between those parts. And when there is a revolute joint here like this one or this one, we are connected the joint actuators where we can move the joints as per our wish. So we've connected a joint actuator, and there are 3 values: angular velocity and angular acceleration. Right now we are not going to deal with angular velocity or angular acceleration. We have to deal only with angles. So, and the pen grip assembly which I have made, where we're gonna fix the pen, I've connected it to a body sensor, where this CG port, that is the center of gravity port, is connected to the body sensor. We're going to plot the movement of the center of gravity, so that it is almost similar to the pen moving. And we have connected it to the XY graph, so that we can plot a graph as the pointer moves, and you can just point this. Okay, we have connected it to a display so that we can see the values, and I've given it a gain of -1 because in my CAD model I have I have mated the base to negative x-axis and negative z-axis, and our the y-axis is perpendicular to our model. So we are going to basically write on xz plane, so that's why I've terminated the y port. So this is our assembly. This is how the Simulink software perceives it. This we cannot just see the assembly as it is, but we can see and simulate it after we press this run button. So, but when we have to give some angles to the joint actuators, which will eventually give angles to the revolute joint. So I have made some notes in this Excel file, and like LTN and S, O likewise. So I've plotted the angles using, I've created a function wherein I've written a code wherein like the analytical 2 code, where if we put the coordinates we'll get the angles. So using this code I've generated the angles for the x and y coordinates and stored them in this Excel file. Like for letter N, and this is the time interval at which this angle must be used, or this at this time interval the angles are executed, and we will see the end result. So in this portion I'll just write q1 equal to 0, q2 equal to 0, so that we create two variables q1 and q2 as we have given to the joint actuators, revolute joint. In this revolute joint I've given q1, and this revolute joint I've given q2 from the workspace, so that it will take the values from the workspace and execute it. So now in the q1 there's this table in which we can put the values of, we'll copy these values and put it here. Okay, and then same will be done for q2. Copy, then I'll paste it here. So we are ready with the letter N. So I've already generated the angles and we are ready with the letter N. And now see how this will work. But the simulation time I've given here as 2, but the total simulation time is 1 as per our angles. So I'll change it to 1, and then I'll just run the code. So let's see how it runs. Now this is our, and how this, see, this is making the N. It's a bit slow because we have taken a very we have taken more time. So see, this N is created. We have plotted the center of gravity of this assembly, that is the pen gripper assembly, and it makes N perfectly. Similarly, we can plot many such things, such as we'll close this, and likewise if I give again, if I give another set of angles, like you can plot NO, like you can plot S as well, but for S, for the curve to be smooth, we need to give lot of angles. So I've taken here a set of 20 angles, and copy it to here in Q1, paste. And similarly I'll copy this set of angles for Q2 here, and then paste it here. Okay, so I've given this, and we'll change this time to 2. This is the simulation, total simulation time for which the simulation will be carried out by the Simulink software, and we'll run it. So let's see if it makes SC. So here we can see that it makes a bit faster than the last time. So this makes an S perfectly, but there are some not as perfect curve we can see, because we need to give a hell lot of angles for the curve to be perfect. So I've given only 20 angles for this curve. So for these angles to plot the S, I'll tell you one idea. To plot the S curve, we need not manually get all the angles, get all the coordinates. As it is on a curve, we will also not get exact integer values, for which I have written a code here in MATLAB so that I can get the coordinate values of the S curve. So I have broken the coordinate portion code into two parts, that is S coordinates 1 and S coordinates 2. For the X coordinates 1, we are going to plot the upper curve, and for S coordinates 2, we are going to plot the lower curve. I have taken r equal to 2 so that actually I have taken half circle values, that is a semicircular values, and we are going to make S using two semicircles. Actually not two semicircles, but three quarter circles. So I'm varying the theta from 90 to minus 180 in the interval of minus 30. So I have stored the values x and y as r sin theta, r cos theta, and x equal to x plus 13.5, y equal to y plus 14.5, and we printed the values. Similarly, I have done it for this S coordinates 2, and the angles, for the angles I have done the same thing, but I have calculated the angle moved by the motors using this analytical formula. Use angle 2, this analytical formula which I have used to calculate the other angular values. So we need not calculate all the integer values, so I'll show you how to plot the circular values, coordinates and angles as well. So I have saved it as S coordinates, and I've got the S coordinates here. I've taken the coordinate value. See, likewise, if we cannot calculate the 11.76949 value manually, as it is not very feasible for us to calculate. And so similarly, S coordinates 2, I'll get the values of S coordinates 2, and S angles, so that I can get the angular values. I will move by the motor 1, by motor 2 for the respective coordinates, and S angles. Yes. So I've plotted and I've taken the angles, stored it in this Excel file, and used this in our portion, and use this in the Q1 and Q2 values. So like this, I have used the values and plotted the circles. We can plot many letters using this formula where there are curves involved, or we can manually calculate if there aren't any curves. We can also calculate angles or coordinates, and calculate the coordinates using the y equal to mx plus c formula actually. So I have also done this. So this was my robotic arm and this simulation. So thank you for watching this. Good night. As this is night. Bye bye.